Thanks for the invitation to give a seminar, and it's a pleasure to give a talk here, and thanks for organizing these seminars. Um, so this is going to be a relatively simple talk, I would say, and it fits the 45 minutes time slot that you told me is the time slot so that people have, if they want to discuss, we have time. So the talk I'm giving is Dark Dimension and the Grand Unification of Forces. It's based on a recent paper, actually, we just put it out this month, with Jonathan Hickman and Timo Weigand and Fengjun Chu. So, so we all know about this amazing hierarchy of various scales that we have in physics. You know, the question that Dirac raised in this context is that why do we have such strange numbers? Some of these numbers is not the way he would have stated it, but there's a version of all these numbers the way he would have stated it. So why is the cosmological constant so small? Or you could translate it to why is the age of the universe so big and things like that. Tau now is 10 to the minus 60 inverse. Mass of the neutrino is 10 to the minus 30. And the QCD scale is 10 to the minus 20 in Planck units. And Higgs instability potential is about 10 to the minus 10. As you can see, there's some kind of a regularity pattern in terms of the exponents. It sounds like there are some simple powers of each other in Planck units. And it was a kind of a question that Dirac raised, is there a relation among these? So, and related to these questions such as what's the nature of dark matter and dark energy, and if they are related, comes to mind. And so the smallness of the dark energy and the weakness of the interaction of the dark matter are prominent features of observations. So this is just, we're just taking these observational facts. And the question is, are there any relation between these features? Now, this is a swampland seminar series. So the idea here is that typically in the swampland ideas, we do not fix the theory. We are only restricting the theories. But we can restrict the theories, but also get information from experiments added as extra ingredient inputs. And that can become much more powerful than restrictions. In other words, restrictions combined with experimental input can serve as, in some cases, as a very rigid possibility. And we will see that this is happening actually in the context of applying the notion of smallness of dark energy to our universe. So the dark dimensional scenario, which was motivated by the smallness of dark energy and combining with swampland ideas, which we did in this paper of 2022 with Miguel and Irene, provides a promising framework to try to answer some of these questions. And so what I'm planning to do here is to review some features of it, and then mainly after I review it, to focus on the prospects of embedding grand unified theories in this context. So that's where we are heading. So what was the basic idea? The basic idea was the distance or duality conjecture that we know in swampland. We originally discussed this with Hiroshi. There are various refinements and extensions and all that, but there's a particular version which is also relevant for my talk here, which is the one with Dieter and with Iran, where we extended it to the case not just for Minkowski's situation, but for anti-de Sitter or de Sitter. So there will be an extra ingredient. What happens if these parameters are small, extremely small, and so forth? And the idea is that you get always a tower of light states in extreme distances, and these are duality. This dual description of the theory emerges from this light tower, as we well know. Goes exponentially with the distance in the marginalized space, the mass scale associated with each of the elements of the tower. So we also use this other ingredient, which we know is true in all string theories, which is called the emergent string proposal by Liller and Weigand, where basically the only towers are allowed are gravitationally, well, they are either towers which are gravitational excitations in a higher dimensional space, where a small dimension d that we are in decompactifies to a bigger tower, or you get the light fundamental strings. So this is all we know in string theory. In all the examples, highly non-trivial statement that this is true in all the examples we know, and we assume this is the case. And if you assume this in the context of the Minkowski space, for example, we find that this emergent string conjecture gives you a bound about, so this alpha cannot be too small or too large. There's an upper bound and lower bound for what this alpha has to be. So that's a very specific range, and this is what string predicts, emergent string conjecture predicts. In the context of de Sitter and ADS, this distance conjecture has a generalization where the smallness of the cosmological constant leads to the prediction of a tower of light states. Now, this power, we don't know a priori. We don't have a bounds on what the alpha is, but we have heuristic argument, which in other words, if you extend the same notion of kind of notions of distance we had in the other cases, applied to this case will give you something like lambda to the alpha, and people have extended this. Iran and collaborators, and as well as we and others have recently extended it and tried to give more evidence for this kind of behavior. So I think we have now more or less solid evidence that this is happening, but we don't still have a good bound on what alpha is. We have a lot of examples in ADS where this is true. In fact, essentially every supersymmetric ADS that is the reliable ones, I would say, have alpha equals to a half strictly. But it didn't have to be, and in some other proposed scenarios where people get alphas, but alpha in all examples known as order 1. So this is the general story for this case, and you can ask, what about other cases? And it turns out that for de Sitter, you would expect a similar kind of tower, similar kind of exponent, but in the case of de Sitter, the exponent cannot be any bigger than a half, because in that case, you have the Higuchi bound if you have a de Sitter type space. And by de Sitter, I don't mean strictly de Sitter. I mean something quasi de Sitter, approximately de Sitter. Alpha should be less than or equal to half if you have an approximate de Sitter space. But you would expect that alpha to be bigger than 1 over d. Now, this requires some discussion here. We are saying that there's a light tower whose mass goes like some power of lambda. So that means that mass tower, at least the lightest tower, should give you the correct or effective description of the theory. And in that language, you expect there to have the loop correction for that mass tower, and you would get something like m to the d. So therefore, that will tell you that alpha cannot be any smaller than 1 over d, because there will be corrections, unless there's cancellation like in supersymmetric case. But in the case of de Sitter, we don't expect there to be one. So this lower bound is motivated from that picture that there's no fine tuning here. Of course, this could be in principle violated if we kind of pushed it and said, what if we did a fine tuning, or what if the situation more fine tuned, and so forth. This needs also a little discussion, because I say that the tower of particles contribute m to the d. You could ask, well, why doesn't the more massive objects contribute, like the Higgs and the other ones which are much more massive? They would also potentially contribute. In those cases, the point is that those are composites in the view of what are the entities that we're talking about. In other words, we should not view them as fundamental entities. And this happens often, quite in nice, simple examples in string theory, where you get other states which are like monopole states or brane states and so forth, which you naively think would have contributed to cosmological constant, but actually in the string limit, only the light string tower contributes mainly. So this is a kind of motivation that even though there could have been other contributions, we expect the composites, they're in some sense morally composites of these light degrees of freedom, and therefore this is the more robust bound. Anyhow, if you apply these to our universe, one finds that the only viable possibility is that this alpha is 1/4, and the only other possibility consistent with our universe for this tower would be that the mass goes like lambda to 1/4, which gives you a mass of the order of 0.01 to 0.1 eV, which means that the length scale associated with it is around 1 to 10 micron or so. Right. So this is the only possibility, given the observation that the Newtonian force law, the 1 over r squared law, works at least around 30 micron. So around 30 micron, we have this working. And so this is at least the lower bound. Therefore, this gives you right on the nose something that's possibly observable with the next round of extensions of this inverse square law experiments. And then one can ask whether this light tower is KK or string, and it's easy to argue that's not a KK tower, because if the mass of the string of the order of electron volt or something, then the gravity is badly violated. The effective theory of gravity is badly violated the electron volt scale, which we know it's not. In other words, you have higher order corrections like R squared, which are only pegged to the EV, and you would get things like black holes produced in the accelerators and so forth, which is not happening. So therefore, cannot be a string tower, and so it has to be a KK tower. And putting all together, you find that the only possibility, if you have n extra dimensions and other experiments, consequences that force you just to have only one possibility, which is one extra dimensions. So you end up, to make the story short, is only one real possibility if you have this, if you have a dark tower of this type with a higher dimensional Planck scale in 5 dimensions, which have one extra dimension, to be around lambda to the 1/12 from this formula, which gives you about 10 to the 10 GeV. So this is the rough picture here. Now, as I say, I have to clarify here, I'm not going to be careful with order 1 numbers. Throughout my talk, I'm going to be, you have to assume there's a factor of 10 or something floating around. I'm not going to be precise with factors of order 1. So the summary is that the dark dimensional scenario is the scenario where we have one extra mesoscopic dimension of length in microns. And this leads to a fundamental Planck scale in 5 dimensions, which is around 10 to the 10 GeV. This is unlike the large extra dimensional scenarios, which was motivated by making the weak scale the fundamental scale, where it would have required m hat to be TeV. Here we are having m hat is 10 to the 10 GeV. So this is not explaining the weak hierarchy. This is not explaining that, and it's not motivated by that. It's motivated by quantum gravity considerations and the dark energy rather than the hierarchy involving the weak scale. And unlike the large extra dimensional scenarios, which requires 2 or more higher dimensions in order to accommodate a Planck scale of the order of TeV, here we have only possibilities 1 extra dimension, and the Planck scale is 10 to the 10 GeV. So we can ask, okay, so let's take this further and see what kind of phenomenological prospects are there for this model. Or standard model of whatever fields, they should be localized in the mesoscopic dimensions, because if they were not, suppose they lived in the full extra dimensions. Here, the 5th dimension I'm drawing by this cigar-shaped object. I have drawn it as a cigar-shaped object because I don't really know the size of the circumferences and so on of this extra dimensions. So I only know that there should be one larger dimension, which I'm denoting by this cigar-shaped object. And we have the brain here, but this, if we were not living on a codimension 1 subspace of this 5-dimensional space-time, if we were living in the entire space, then you get for every particle that we have, we get a tower of particles in the scale given by electron volt or milli-electron volt, and that certainly is not possible because that would violate experiments badly. So we better be localized in the 5th dimension in some region. Any questions before I proceed? Okay. Now, in this scenario, the natural candidate for dark matter emerges because, first of all, the only way to accommodate it's natural because we said that there is a dark energy small, and therefore there's a tower of light particles. That's how the distance conjecture tells you there's a tower, and it's very natural to use that tower for dark matter. So the dark matter is automatically fixed, and the fact that that's another feature of the swampland distance conjecture, the tower is always weakly coupled, which is a feature of dark matter. So this already makes one prediction without any detail, is that dark matter has to be gravitationally coupled, like the gravitons in the case of the distance conjecture. So they are already weakly coupled without actually any assumptions put in by hand, consistent with observations that dark matter are weakly coupled. But that also means that the full cosmology cannot start from equilibrium where everything was at equilibrium at a given time, because if it was starting cosmology at the 5-dimensional equilibrium, then you would be left with a relic of a huge number of tower of light milli-electron volt states, which are in contradiction with the fact that the number of effective in the regular cosmology is 3, approximately 3. So that would violate that bound. And so we cannot start from that. So the only way to accommodate our cosmology in this scenario, the Big Bang cosmology, at least the post-Big Bang nucleosynthesis, is that you have some initial temperature on the brane. And it turns out that the magic temperature that you want to start here ends up being around GeV scale. If you start with the GeV scale, as we showed within a number of works with a large number of collaborators here, these various papers describe this scenario of how you can realize the dark matter as created from temperature on this brane around GeV. The GeV gives you the right amount of dark matter. And the elegance of it is that you don't impose by hand how you create it. It's fixed by Einstein's theory, namely energy momentum tensor couples, energy momentum tensor on the brane, which I'm denoting by X, couples to graviton, which also propagates in the extra fifth dimension, which I denote by Z. So this interaction gives rise to creating, if you have a web for T mu nu, which happens when you have a temperature, when you have a thermal background, automatically excites the graviton modes in the fifth dimension. So if you expand H mu nu in the graviton modes, which the harmonics of the H mu nu in the extra dimensions, you'll expect to have the masses of these extra modes to go like n over L, where n or n times the kk scale of this, which is the electron volt or milli electron volt scale, as a tower. So you'll excite them. So you have a huge excitations like this, and they play the role of the dark matter in this scenario. So you have some initial temperature where the hot brane that we have excites these graviton modes, and it creates some dark matter, and they will basically look like a situation like this. So you think about our universe as some kind of a slice in the 4+1 dimensional, our brane as a 4+1 dimensional visible universe, as a slice in the 4+1 dimensional universe, like what I've shown here. And when it was hot, it was creating these kk excitations, which are in the bulk. And as the universe cools down, the radiations in our universe cools down, then it turns out that this little remnant of what it was emitted becomes dominant because they are massive, and they scale much slower in density. They go lower in density down, and they provide the right abundance for the dark matter. So this gives you an interesting dark matter candidate with specific signature, because because these are kk gravitons, they have to decay, and the decay is gravitational, so we can kind of predict how the decay goes. We just have to make an assumptions about whether they violate the quantum number of the kk quantum numbers they have. And it turns out it should be very little violation of the kk quantum number for the dark matter to decay gradually. So that means the extra fifth dimension should be relatively smooth. And this decaying gradually would be a distinguishing feature of this model compared to lambda CDM, where in this case, as they decay almost at threshold, but you'll get a slight kick from these decays, and this decay, you can kind of estimate the decay speed, the speed of the remnants, and that will give you a slight difference in structures that we are actually studying, which we studied somewhat, but now we are studying in more detail even now to see what precise distinctions there is with lambda CDM. There are other candidates for dark matter in the form of primordial black holes, and this dark dimensional scenario has been also studied from a totally different angle by Ankerdougi, Antoniadis, and Lust, from a totally different perspective, where they have, for example, they study inflation in these 5D models, as well as dark matter being primordial black holes and so forth, which is rather different from this cosmological scenario I was telling you about. Anyhow, so this is the work which has already been done, and this is now where I want to basically shift gear to the recent work. So this was a kind of like a background, which is almost half of my talk, but now I get to the main thing I want to talk about here, which is grand unification of forces. So the question is, do we have a grand unification of forces? Now, the standard matter fields neatly assemble to simple representation of a bigger group, right, like SU5 and SO10. And this hints at the unification of forces similar to the Georgia-Glashow model of SU5, and many other examples exist also. But it's hard to not be impressed by the elegance of unification, of simplicity, of combining the matter representations that have been discovered into irreducible representations of these higher groups. So, it's just elegance tells you something like this may very well be true. And if you look at the scale here, however, you see that if you at least run the couplings from the scale we are at, you find that the unification of these scales is not quite great. It happens in the range around 10 to the 14 to 10 to 16 GeV. And so people, hope maybe you have some other matter fields in the middle, maybe some string tower here or there to change this unification to meet together at some scale around 10 to 16 GeV. That's the hope that people have considered in the context of string theory realizations. But we expect that if there is a grand unification of forces, the GOT scale should be bigger than 10 to the 16 GeV. In other words, the unification of the forces cannot bring the scale down too much. And the reason is that in the grand unification models, you invariably have extra gauge bosons whose mass is the scale of breaking of the GOT symmetry. And for example, in the SU5 model, you get these triplet, doublet gauge bosons. And this is, for example, one of them is called the X boson in the SU5 GOT model. And so these mediate proton decay. And if you try to fine tune and so on, you can try to evade it, but that will look really fine tuned. But in more natural setups, you naturally end up saying that the mass of the X boson cannot be any lower than 10 to the 15 to the 10 to the 16 GeV if you don't want to violate observations of the longevity of the protons. In other words, the proton decay bounds imply that the mass of the X boson should be bigger than 10 to 15 or 16 GeV. So now you can ask, what about string theory? Well, string theory does not demand grand unification of forces. In fact, in almost all string theory models, the unification, if it happens, it's in a subtle sense. That means that the forces typically unify in a higher dimensional sense, not in 4D sense. So there's some symmetry in if you go a little bigger in dimension, if you delve down into dimensions, then you can see some hints of a unification typically. But there are also examples of string theory realization of standard model matter content, which at least formally don't seem to come from any unification, at least not naively. So this could say, even if you don't have a grand unification, that's perfectly okay with quantum gravity. So it's not a swampland statement. It is not that it had to unify. At least it appears that we have perfectly fine models for which the standard model fields emerge with no apparent unification whatsoever. So I'm not stating this, therefore, as a swampland statement. You could or you could not have GOT is up to you, whether you want to assume there is one or not. A priori, we don't know. It's elegant. It would be pleasant to have it because of this simplicity of fitting, and I think it has aesthetic feature, but we are not forced to it. So the aim of this talk is basically assume it happens, even though it's not totally forced on us, and see whether or not it can be accommodated in any way in this dark dimension scenario. So naively, we have immediately run into a contradiction with the GOT scenario. As we said, the standard model brain is localized in the fifth dimension, and the X boson that we are talking about should live on it. But 5D Planck scale is around 10 to the 10 GeV, and we know that mass of the X boson is 10 to the 16 GeV. So if you have a particle X boson on our brain, then its mass is bigger than the Planck scale mass, and therefore you would expect it to form a black hole in the 5D sense. And therefore, you would expect this object not to be the regular gauge boson that you want to have. After all, it would be shielded by a horizon and all that stuff. So therefore, this would not behave like what we want. Therefore, the fact that the mass of the X boson is much bigger than the Planck scale tells you that you want to do something a bit different. But what? What can you do? Well, as we know, there are objects in our universe whose mass is bigger than the Planck mass, and these happen to be non-black hole also, a lot of them, including us here. And therefore, it's natural to ask, could this object be extended in the fifth dimensional sense and still be particle in the 4D sense? Now, you see, it could be a particle in 4D sense because 10 to the 16 is less than the 4D Planck scale. So that's not an issue, but it might have to be extended in the 5D sense, because in the 5D, the Planck scale is already 10 to the 10 GeV. So to avoid this idea that the X boson is a black hole, we were forced to assume, therefore, that the X boson is an extended object in 5D, but localized perhaps in 4D, like the particles that we want. In other words, X boson has to be a string.
Cumrun, may I ask a question?
Yes.
So in this sense, in this scenario, where does this 10 to the 15 or 16 come from? Because
it's not coming anywhere. I'm not putting it at all. I'm just so that was so going back to the philosophy here is that we are using swampland ideas, but also instructed by experiments. What are the bounds?
Right.
We are not deriving it by unification of scales.
Yeah, but I guess 10 to the 15 or 16 assume that there are no sort of additional thing happening between us and the unification scales that to change the RG flow, right?
Correct. So in other words, you're, as in all string models, we always on a limb to try to predict what happens because we have to know all the corrections, which we don't know. So here I'm not saying this unification will happen. I'm just saying suppose this naive picture somehow survives the flowing of the coupling. This naive coupling flow makes some sense. So
you assume that the scenario of merging of coupling constant takes place even beyond the energy scale.
Yes, I will come to that. Very good question. So one naively thinks, and that's a very natural question, you cannot talk about scales bigger than 10 to 10 GeV if the Planck scale is 10 to 10 GeV. So what do you mean by running of the coupling?
That's my question.
At this point, after I present this. So let's sidestep that question for now.
Okay,
so
thank you.
That's a good question. We'll come to that.
Can I ask a question?
Yes.
Minimal SU5 gut is already ruled out experimentally, no, because of proton decay.
So it's not a minimal SU5 by any means, for sure.
Yeah, so if it's not minimal, why don't you just forbid proton decay with some U1 gauge symmetry?
It could be many things, but I think that you can try to, I mean, typically the triplet doublets exist, and you can try to put extra symmetry preventing proton decay. You can try to avoid it in different ways, and therefore there will be no bounds whatsoever. But I think the more natural thing is to try to take the spirit of the grand unification in the usual sense and see what we end up with. So that's my philosophy here. Namely, I know that you can tune this or that to avoid this problem or that problem, but I don't want to go too far off from the usual scenarios. But I know that this is not the standard for the SU5, but it could be unification to a 5D SU5, for example. That's the way I'm thinking about it. That's what happens in string theory typically. When you try to go to higher dimensions, you unify in higher dimensions. So I'm thinking of a 5D or SU5 morally. That's what I'm thinking. That could happen. There's no a priori thing wrong with that.
Yeah, you're just putting a very harsh constraints on yourself, I would say, because I would just say, well, we know minimal SU5 is ruled out anyway experimentally. So,
yeah, you can say that.
I think we have to solve this problem, which we know is already So.
Well, one could say that. In fact, even putting gut is a harsh thing. You say we don't have gut. That's a harsh thing too. So I'm just trying to see as much as possible run with the spirit of the gut scale, being 10 to the 16 GeV, and see where we get. That's basically the thing I'm trying to do here.
Okay.
But I'm sorry, I'm not trying to construct such a model, by the way, just to be clear. Yes.
Yeah, just follow up because I don't remember well, like the experimental bounds for to avoid the proton decay. This bound of 10 to the 15 GeV for the mass of the boson is only for SU5 or also applies for
it applies essentially to a garden variety of theories. You can try to block it by some extra symmetries which prevent it, like the U1 that Eran is saying, but you need to do something like Z3, U1, some extra symmetries to prevent proton to decay by hand. So in other words, I call those models contrived, basically trying to just solve your problem rather than go with what it comes. So that's what I would call that fine tuning, if you want to do it that way.
But if it's a larger gauge group, you also have these bounds on the
probably SO10 and all that. People do have it. Again, in these models, you can try to make some assumptions to try to make it alleviate the issue. So that's not the issue. But anyhow, our model is not 4D gut anyhow. So as Hiroshi said, at best, these would have run, even if it could go past 10 to the 10 GeV, and it could have easily unified to 10 to the 16 GeV or 17 GeV, who knows? So a priori, we don't know. So therefore, that's perfectly okay. So then we can ask, so what do we know? We know that the X boson has to be, since it's in 5 dimension and it's extended, at least from the 5D sense, it's like a string. I don't mean that X boson is fundamentally a string if you include the internal compactification and all that. It could be like a higher dimensional brane wrapped around some other cycle, but by the time you think about it projected to 5D, it should look like a string. That's the only option. You have 1 dimension left only. So the X boson should be, in the 5D sense, like a string. Then
sorry, can I ask a quick question? So could it also be like a bound state of several particles, like an atom that's also extended? You could imagine like a very big atom, but the energy doesn't scale like a string.
Well, we're trying to say that this does not decompose to pieces. Otherwise, it wouldn't behave like a fundamental particle like a gauge boson. So no, I'm not assuming this is decomposable. I want to have, at the scale of the SU5, it is at the scale of the gut. I mean, I want to have an indecomposable object, a fundamental object. So it's not like atoms. No, atoms will be vaporized by the time we get to that scale.
No, but it could be, so it has to be an extended object to avoid the
transport. Just like string bit model. Strings you can think of made of bits, but it cannot be broken up. That's what I'm saying. So in that sense, it doesn't matter how you want to think about it. It is an object like a string.
I just mean that there could be a more general dependence of its mass with this length than linear, perhaps.
No, but the atoms example that you're saying is also linear. Namely, the mass of the atoms play the same role as tension. If you put them together.
If you imagine many, but maybe it's like a bound state with some potential, but okay.
Yeah, well, anyhow, so the most natural scenario is that the strings is like a string with the regular properties of a tension and all that, mass per unit length. It's a one-dimensional object, there's a mass per unit length. Now, before we get to something, we want to ask, what is the size of the standard model brane, the gauge bosons and the matter fields? We don't know. A priori, they could be Planckian in 5D sense or whatnot, but we don't know a priori. But even that, we need to be a bit more careful. There are different parts of the standard model brane. First of all, you can ask, where are the gauge bosons in the standard model brane? So the gauge bosons would be localized in some region. Let me call the diameter of that region in 5D sense LG. This is the length scale for the length or diameter for gauge boson. The matter fields will be localized in some other regions, diameter Ln. We expect that Lm to be less than Lg. The reason is that the gauge fields act on the matter fields. So therefore, by definition, the gauge fields, the matter fields has to be experienced in the gauge fields. Therefore, Lm should be less than Lg. This is, of course, the kind of things we already see in string theory, where you have the branes or d-branes and so forth, which gives you gauge bosons, and the matter field typically comes from intersectional regions. So this is a very natural thing in the context of string theory, but it's also generally expected to be like this. Now, X boson is going to be part of the gauge field, so therefore it should be part of this. So its diameter, whatever that region is, should be less than the diameter of the gauge boson region. So Lx should be less than or equal to Lg. So that's the basic aspect. So we have potentially three parameters here: the size of the gauge boson's localization, the matter fields, and where the X field boson is, which presumably is not too different from Lg, but anyhow, we put it Lx here. There are experimental bounds. So first of all, the diameter of the gauge bosons, if it is too big, you will get a tower of KK mode of gauge bosons. Like you have W prime and masses and the Z prime masses and so on in the range of the corresponding 1/r of the size of this extra gauge boson. And this cannot be too light because there's already experimental bound, for example, on W prime of the order of a few TeV. So therefore, the Lg inverse should be bigger than or equal to 1 to 10 TeV. The masses that you get cannot be any smaller than this range. There's also another bound, which is on the Lm inverse should be bigger than 100 TeV. That means that the matter region should be even much smaller than the 10 TeV range inverse. And the reason for that is that so this is actually probably not very familiar to most string theorists. So I want to describe this because actually it's an important fact that people in string theory phenomenology, apparently, at least as far as I know, have not made a note of this fact. That so let me explain what this basic statement is. So as you know, there are different flavors in the standard model, and in principle, you could imagine, for example, going from up quark to the charm quark by some Z boson neutral current like this emission. And experimentally, this is highly suppressed, and it is not. There's bounds on these. So in other words, this is called the flavor changing neutral currents. Neutral currents which change the flavors is highly suppressed. Now, Jim mechanism explains that. So what is Jim mechanism? Jim mechanism says in the QCD Lagrangian, if you forget about the mass term of the quarks, which are different, there should be an approximate SU3 symmetry, the flavor symmetry. So if there's a flavor symmetry, that symmetry actually can be used to show that there are no, if that SU3 symmetry was exact without the masses for the quarks, then you could show that there is no flavor changing neutral current. So experimentally, they have observed bounds on the flavor changing neutral currents, which tell you that this symmetry, SU3 symmetry, is good up to about 100 TeV scale. That means that if you ignore the mass of the quarks, the mass of the fields, the standard model fields, which come in 3 generations or 3 families, they should be symmetric, like an SU3 exchanging them. However, in string theory, we get flavors from 0 modes of Dirac operator, and therefore the Jim symmetry tells you that these 0 modes should have an SU3 symmetry. So if you have 3 0 modes, they will give you your generations, but there should be an approximate symmetry exchanging them, but that will be broken by the size of the KK tower of the region where the matter field is localized, and therefore you expect that the SU3 flavor symmetry is broken by LM inverse effect. So therefore you would expect the LM inverse to be bigger than 100 TeV to avoid the bounds that people have already observed for flavor changing neutral current. So this, regardless of this scenario that I'm talking about or not, these are bounds coming from experiments, and we should, as string theorists, we should be aware of these facts, that the gauge bosons, wherever they are localized in our universe in higher dimensions, this should satisfy this bound. So we expect, without any kind of details, we expect a situation where if you talk about there should be some kind of perhaps a hierarchy. Well, the gauge boson region is the biggest one. LG is the biggest one. And then there is a region, that's the white region of the brain I'm plotting. LM is the region where the matter field is localized. That could be smaller than LG. And LX should be less than LG, but maybe of the same order. We don't know. And these are, all of them, of course, are much smaller than L5, which is the size of the extra fifth dimension. Now, before I go that, what do we expect this length scale of the gauge boson to be? In string theory, we don't have any a priori expectation, but actually it turns out phenomenologists already in the late 70s, the 80s, 90s, etc., have written a large number of models where they talk about gauge bosons in higher dimensional scenarios. And in those cases, they invariably are interested in a situation where the size of the gauge boson, the diameter of this region is in the order of 1 to 10 TeV. So let me explain how this comes about. So these ideas started, I think, in the phenomenology literature in a situation called the gauge-Higgs unification by Manton in '79. So that you see the date, these are really before, a lot of developments in string theory. They were talking about what if the Higgs field is a component of a gauge field in a higher dimension. Now, this is, of course, for us, is very natural in string theory. That's the way we get our matter fields, is components of gauge fields in higher dimensions. So that's very normal. But this idea came about from this picture that maybe Higgs can be viewed as a gauge field, and so we can have a unification with gauge fields. So that idea is certainly natural for string theory. But actually, then later, this picture became natural to try to come up with what is the size of this kind of description. And the idea was that in this context, the gauge field, the Higgs field, may be related to the holonomy on some kind of a zero mode of this gauge field in this higher dimension, which is some kind of or approximate holonomy in this higher dimensional sense. So we can identify if you have a Higgs field as the holonomy, which is, so if you have a gauge field times Lg, so you have a holonomy of that field, which is of order 1 parameter, up to a coupling constant is given by the Higgs field.
Sorry, can I ask a quick question?
Yes.
Yeah, before LG was like the size of the blob of the standard model brain, and here now it's like more like the size of the circle where you're taking the holonomy, right? So they're like slightly
No, size of the brain in which it's the same, still the same thing. So let me just be more clear. Suppose that the region is a little tube, like a cigar or like a sphere squashed or something. Okay. So then you have gauge fields on this.
Okay.
So you can have a component of the gauge field which is not quite a zero mode, because there is no zero mode, but be slightly massive. So you get a mass in that context of the order. In fact, that's where I'm heading, of the order of the KK scale. So in fact, what I'm trying to exactly argue here is that this will naturally give rise, in particular, if nothing else, through Casimir effects, to masses of the order of set by the scale 1 over Lg to the 4th. Or said differently, you get a mass for the Higgs, which is of order of KK scale here, up to a string coupling, up to the coupling constant in your theory. So if you want this to be, let's say, in the 100 GeV range, 100 to, let's say, 100 to GeV to 1000 GeV, then you're basically saying, because you have lambda is 0.1 or so, let's say, it will give rise to Lg inverse of the order of 1 to 10 TeV. So
I think, Cumrun, I think Miguel is asking that holonomy is usually associated to pi1. So where is the pi1 in this case?
I try to explain. So think about the gauge field. There are two ways to look at it. Either there is like a circle, which is a possibility, which I'm not assuming, but you could in principle say there is a holonomy on the circle. But more generally, you have a gauge field living in 5 dimensions. You take the harmonics of it. The lightest harmonic of a gauge field, I'm calling the Higgs. It's not zero mode. I'm calling the holonomy, but it's not the holonomy. But it's coming from the zero mode. You're just expanding the A mu in the 5th dimension in terms of its harmonics. The lightest mode of that, which if it's not zero, whatever it is, you could call it the Higgs. But at any rate, either picture would suggest that the mass scale associated with it is 1 over Lg. That's basically what I wanted to bring here. So this gives you a natural description of mass of the Higgs being Lg inverse. This is why phenomenologists like this kind of model. The reason is they did not understand how you can have a naturally suppressed Higgs mass. Their whole idea was that if the Higgs field is a gauge field, then you cannot write A mu squared in the action. It breaks the gauge invariance. However, if it comes from a higher dimensional theory coupled to things, they could generate effects like the Higgs field would, like the holonomy would, and gives rise to a mass in the effective Higgs field. So that's the idea they had. And this kind of picture was what Manton et al. And others developed. And this is sometimes called the Higgs as the pseudo-Goldstone boson, because this shifting of a gauge field is a pseudo-symmetry. And sometimes this is called the composite Higgs models in this context, where you can think about the Higgs as holonomy, which is made of integration of the loop around this circle, or the little Higgs models, where you take the combination of these quivers, which mimic by deconstruct these extra dimensions. So all of these basically do the same thing. In the context of this translates to the statement that in these models, if you have a gauge boson of the scale of the weak scale, you could potentially naturally explain a Higgs of the same mass scale. That's what I want to say. Okay, I have said this, but I'm not going to assume this at all. I just wanted to give this as a background to you. So if you didn't like what I just told you, if you found this is not natural or something, you can forget about it. My talk does not depend on this at all. Okay, so let's move on. So you can this was kind of informational about the history of what people have done. A priori, we still don't want to assume anything about the size of Lg. We don't want to assume it's 1 to 10 TeV. We don't want to assume anything. We only want to assume that the Lg inverse is bigger than 1 to 10 TeV, just because that's the experimental bound.
One question before you go on, just out of curiosity, like if one takes this scenario for the mass of the Higgs boson, is it really natural in the sense that, like, if one considers then all the couplings, no, with all the matter fields and the self-coupling and so on, can give rise to a mass larger than this. Or
people have done, in fact, people are still writing papers on this gauge unification, and they have to put some parameters in a Lagrangian, which is like 10 to the minus 2 or something. So there's some parameters that they have to fine tune, but it's not like 10 to the minus 80 or whatever, 10 to the minus 20 or whatever. It's not that kind of fine tune. It's better situation. The phenomenologists are generally resistant to this because there are extra dimensions. So that's why the little Higgs model said, oh, you don't need the extra dimensions. You can kind of make extra dimensions by deconstruction, like extra quivers and so on. So that's why it's not necessarily the mainstream, I would say, of phenomenology, but it's an idea that they have toyed around with.
But the natural result then is not the cutoff, like the Calusa, like just
that's
this
right. So that would be natural in that sense. So even if you have a localized Higgs field on a gauge field, this will give you a natural scale. So that would be the natural explanation of the weak scale for them. Okay, so but anyhow, I'm not going to assume this for my talk. So let's go back with no such assumptions. LG inverse experimentally is bounded to between 1 to 10 TeV. LM inverse is bounded to be bigger than 100 TeV. And LX inverse should be bigger than LG inverse, and that is, as I said, bigger than 1 to 10 TeV. This is all I'm going to assume. In fact, the LM bound is not going to play much role for me. So I'm basically going to focus on the first one, which is on the third one, which is basically the last line, basically. LX inverse is bigger than LG inverse, bigger than 1 to 10 TeV. Now, so in string theory, just to give you a picture of what I have in mind for string theories, we expect a picture like this. Like you have, you have a region, so like you have SU3 from 3 branes and SU2 from these 2 branes, and they meet at some place where you give you standard model field like triplet, doublets, and so forth. And 3 and 2 are kind of parallel, but they're kind of separated in the extra fifth dimension by some length scale Lx. And you have a string or something between them, which provides that extra mass for the X boson. And if you zoom out to the scales much bigger than this, you see a unification. That's the sense in which we have that statement. So the first partial answer to the statement is that here, notice that there's nothing wrong here with saying that Lx, which is much smaller than L5, could potentially realize a mass scale much bigger than the gut scale, just from this picture. Forget about the running. In other words, there's no a priori problem in string theory to have a very small Planck scale if you have a large extra dimension in this form, as long as you have this tension here suspended like this. Now, we have some bounds on Lx, so let's just see what kinds of bounds do we get. Since X boson is a string in 5D, its mass is given by T times Lx, and T is the tension of that string. Experimental bounds due to proton decay tell you that the mass of X, which is T times Lx, is bigger than 10 to the 15 or 16 GeV. On the other hand, for the X boson not to be a black string, the tension cannot be any more than 5D Planck scale. Otherwise, you get a black string, again, the same problem we had before. So the tension of this string is less than 10 to the 20 GeV squared. And the length of the X boson, as we already said, is less than 1 to 10 GeV inverse, 10 TeV inverse, which means, to be conservative, Lx is less than or equal to 1 to the 10 to the 4th GeV. So that then, if you just put these together, since the mass of the X boson is the product of these guys, and each one of them has an upper bound, that means the product has an upper bound. And the product upper bound gives you 10 to the 20 GeV over 10 to the 4, 10 to the 20 GeV squared over 10 to the 4 GeV, which is about 10 to the 16 GeV. So this gives you that this model would predict that basically I'm using now here gravity statement. I'm using quantum gravity to say that otherwise you will not be able to get the object. The highest tension you can have for any object which is not a black object is a Planck scale. So I'm using that fact heavily here. So this forces you to have an X boson mass to be of the order of 10 to the 16 GeV, because that would otherwise violate the experimental bound. We already said mass of the X boson is 10 to 15 to 16, and here we are saying it cannot be any higher than 10 to the 16 GeV. Therefore, mass of the X boson is 10 to the 15 to 16 GeV, no higher. And moreover, all of these inequalities that I was writing here should be equalities approximately, because this ended up being equality. And therefore, the size of the gauge boson brane inverse should be of the order of less than an order of 10 TeV. And the tension of the string is the 5D, approximately close to the 5D Planck scale. So this is already quite a non-trivial prediction here, that just by trying to realize this, we will get this limit. We will thus be making the prediction that the dark energy and swampland principles, which led us to the dark dimension, is compatible with GOT, at least with the simplest GOT, let me say, if we impose that it fixes the diameter of the gauge boson to relate to the weak scale. Now, so surprisingly, we ended up with a weak scale. The LG inverse was 10 TeV. We didn't put this by hand, but it came out to be. So this is actually quite amusing, because this goes into the same range of parameters that people trying to explain the electroweak hierarchy had imagined in terms of the realization of the gauge bosons in these extra dimensions. It predicts that unification has to happen around 10 to the 60 GeV and no higher. And therefore, the proton decay cannot be much longer eluded, namely up to the next scale, it should be in the 10 to 16 GeV scale for X boson. Now, so this comes back to now the question that Hiroshi was asking. So the running of the coupling constant past the energy of the 5D Planck scale, 10 to 10 GeV, is obviously unphysical. In other words, if you take two gauge bosons or two particles, whatever, charged objects, quarks, etc., and shoot at each other at a very high energy, 10 to the 10 GeV, above that you will form a 5D black hole. So therefore, there's no notion of running the coupling in that sense above 10 to the 10 GeV. You form a black hole. So the notion would not seem to make any sense. However, as we described in a recent paper, it turns out that I forgot to put the reference in this paper. There's a paper we wrote with Bedroya and my student David, where we showed that the lower dimensional physics has a hard time seeing the higher dimensional physics. By that I mean the higher dimensional Planck scale will be invisible to the lower dimensional physics, namely the energy scale in which you create a black hole from the 4D sense will not be, in other words, in our universe right now, we could easily have a 10 to the 10 GeV with no problem, with not being observed in the effective terms that the gravity sees, because the formation of this black hole is a Gregory-Laflamme transition, which is not seen by the Lagrangian in the 4D sense. So the Gregory-Laflamme transition is a transition which the low-energy Lagrangian misses naively. If you perturb around the Lagrangian, it is the first-order transition, and you don't see it a priori from the language of 4D. So that could potentially explain why the naive GOT formulas that people are using, which is not sensitive to this thing, naively predicts this scaling unification. Of course, going back to the picture I was drawing, there is nothing wrong with saying that there is a GOT in 10 to the 16 GeV. Namely, I just drew a situation for you where you have, it's not a running of the coupling constants, but for sure, the X boson mass is 10 to the 16 GeV, and it's bigger than the Planck scale, and there's no problem. And if you go to the scales, which are the distance scales, which are much larger than the size of the X boson, you will see an SU5 unification. That's the sense in which you have a unification at higher than the Planck scale. Namely, you have to allow these extended objects to play a role. So that's the sense. That's the only sense in which in this dark dimension scenario could realize this. Of course, Hiroshi's question is still valid in the sense that even if we assume that it's hard to see the higher dimensional Planck from the lower dimensional running, it remains to be shown that whatever is in between will not change that 10 to 16 to some other thing, even the naive unification. So I'm not deriving that. I'm not claiming it had to be or whatever, but it's quite amusing that there is a potential scenario where this 10 to 16 GeV would make sense. Now, after all this, I'm still remaining agnostic to whether we have GOT or not. In other words, I'm not saying we should have GOT in the minimal sense that I just told you, but I find it quite amusing that just the very assumption of the existence of it in the simplest scenarios together with the predictions of dark dimension, which is rooted in the smallness of dark energy, somehow gives you the scales that are already 10 to the 16 GeV pops out. And that to me is extremely interesting because we did not put this number by hand. It just came out.
Cumrun, can I ask a question?
Yes, but maybe let me just finish this one because I
sure,
think I have
yeah,
more
go
minutes. Then I'll be happy to answer. Let me just actually say that what we are just showing is that the mere assumption of the existence of grand unification tells you in this context that we ended up with a weak scale, which is 1 over LG, and the gut scale, which is LG. So the weak scale is like momentum modes, like the Higgs fields that I was telling you about, as in the holonomy, and the gut scale is like winding modes. So the LG and 1 over LG symmetry in this case is related to gut versus weak. So you have both scales coming from the same parameter LG up to the guts, up to the Planck scale. So there's only one scale determining both in this case, which is the LG, the weak scale. Now, this, of course, predicts a KK tower of standard model gauge boson is 1 to 10 TeV range if it's true, assuming that there is a gut. And we have now more reason to look for proton decay as well. So presumably in the next round of high energy colliders, you could look for such towers of particles. Thank you. So I will stop.